Hello all. In this particular lecture, I'll tell you about the Navier Stokes equation and the problems which we face while solving these Navier Stokes equation and why they are so difficult. In fact, why they are not solvable till date in their holistic form, in the closed form, and what are parallel flows and how parallel flows makes these equations simple for us. So now, right now I have written Navier-Stokes equations in Cartesian coordinates, that is x, y, z. You can also write them in polar coordinate, doesn't matter. But for the sake of understanding, this is a good point. Now, if you look this particular equation, the left hand side is nothing but the mass into acceleration per unit volume, and right hand side is basically the force per unit volume. So they are nothing but the momentum equations. If you look them closely, then you will be able to understand that these parts, these are nothing but the parts which create problem. Why? Because these are non-linear terms here. Why? Because a differential equation, whether it is partial or ordinary, is said to be non-linear partial differential or non-linear ordinary differential equation when the coefficient becomes the function of the dependent variable, and here dependent variables are u, v and w, and we can see that velocity terms are lying in front as coefficients, and hence the left hand term, specifically the convective acceleration term, becomes non-linear, and hence the Navier-Stokes equations becomes non-linear. That is the reason why these equations are difficult to solve in their closed form. So now here we introduce this term known as parallel flow. What do you mean by parallel flow? Parallel flows are those flows. Parallel flows are those flows where the only existing velocity is 1. That means, let's say u is the only existing velocity. That means u is not 0 and other terms will be 0. Here, by saying that u is not 0 doesn't mean that u is the only one. You can say v is not 0 but u and w are 0. It doesn't matter. But the main important thing is that along the direction of flow, that is the only existing velocity and others are non-existing. So now if this is the case, then what will happen? The partial differential equations will try to converge towards ordinary differential equations. And here comes the three classes or three milestones or three problems in which we can solve these equations very easily. So what happens when we do this? When we say u is not 0 and v and w are 0, then if you look this left hand side term, if I say u is not 0, then this term will v and w are 0, so this term will vanish, this term will vanish. Likewise here, this so the terms which are containing v and w, they will vanish. And apart from this, if we consider some special assumptions, then this equation or these equations will get converted into ordinary differential equations. So in the next lecture, what we'll do is we will try to solve one such a case which is known as Couette flow. Very important when it comes to laminar fluid flow or viscous fluid flow. Okay. So in the next lecture, what we'll do is we'll try to understand that what is Couette flow. So in this lecture, you have learned that what is the problem with the Navier-Stokes equation and what are parallel flows and how those parallel flows help in solving these non-linear partial differential equations. Thank you very much.